Hi everyone, welcome back again from our 5-minute break. Now we're going to talk about multivariable integration. So we just talked about multivariable derivatives. We can obviously go the other direction as well, so we get multivariable integration. And so this is going to be the final part of our lecture today. So it's just going to be the exact opposite of taking our partial derivatives. So let's go ahead and get started. And I'm only going to talk. I'm mostly going to talk about definite integrals because it turns out that indefinite integrals are harder to make sense of when you have multiple variables. But so now, if we have an ordinary, so I have both of these on here, but here at the top we have a ordinary integral, right? So we have several different pieces here. So we have this piece here, which is just the variable of integration. We have this piece here, which is the limits of integration. And another way of writing this, so sometimes it's useful to write this out explicitly saying what the limits are. So this is x equal a, x equal b, f of x dx. Okay? So now, what happens if we do this twice? So if you have a multivariable function, you can do it with respect to either x or y, or do it with respect to both x and y. And when you do this, what ends up happening is, well, it starts out easy. So first, you have integration by x. So integration over, let's say, do over the x variable. And then you might do it again and integrate it over this y variable. So integration over y. And sometimes it's useful to write this out a little bit more explicitly. Sorry, I used up my color green blue, so I need to use a different color here. This is the integral for y equal a to y equal b, integral x equal c to x equal d, f of x y dx dy. And then there are obviously two pieces, so you do this piece first, and then you do this piece next. Okay, so that's just a notational question. So this is what our notation means. And one of the things that is really cool about definite integrals, and this is part of the reason we're using definite integrals here, is definite integration removes the variable. So what do we mean by this? Let's give a couple examples. So if you have the integral from 1 to 2 of x squared dx, that's equal to 1/3 x cubed from x equal 1 to x equal 2. So it's equal to 8 over 3 minus 1/3, which is equal to 7/8. Note that there aren't any x's. There aren't any x's anymore. And this is different from doing indefinite integration, because if you just did integral of x squared dx, that'd just be 1/3 x cubed plus c. And so your x is still in there when you have indefinite. So when you have indefinite integral. But when you have a definite integral, it removes it. So your answer no longer has any x's in there. And so this is super helpful because it means that when we do the integration over x, we no longer have any x's left. We can do this again. You can do this with other variable names. So let's say you integrate from 1 to y of x squared dx. Y here is just some other arbitrary constant, right? So when you do this, you get 1/3 x cubed from x equal 1 to x equal y. And this is equal to y cubed over 3 minus 1/3. So you'll notice that you no longer have any x's in the expression after you've done a definite integral by that variable. And this is super important because this means that when you're doing this multiple integration, in each step, you're basically removing one of the variables from your expression. And that gives us a strategy for how to do these multiple definite integrals, which is you first integrate by the inside integral, assuming all the other variables are constant, and then you integrate by the outside variable to get the answer. Okay, let's try this out. Or let's try this out together before I make you guys do one on your own. So let's say that we're going to start out with this interior piece. So let's start out in this blue interior piece. So the integral from -1 to 2 of 10xy squared dx, well, that's equal to, here we're going to treat y as a constant. So treat y as constant. you treat y as constant, so this is going to be equal to 5x squared y squared from x equal minus 1 to x equal to 2, which is going to be equal to 20y squared minus 5y squared, which is equal to 15y squared. Okay? And then you might do this other piece, which I'm going to put in the outside piece, which I'm going to put in green. And so then the integral from 0 to 2 of 15y squared, since we already did the inside piece, dy is going to be equal to 5y cubed from y equals 0 to y equal 2. So this is equal to 5 times 8, which is equal to 40, which is our answer. Okay, so note that our original function was a function of both x and y, and now we've done this double integral. We've integrated out over both x and y. And the way you do that is you first do the inside piece of setting the outside variable equal to the constant. So you do the inside piece, integrate with respect to x, setting the y equal to the constant, and then you do the outside piece just as a normal integration, and this is a double integral. So let's try this out, shall we? So I want you guys to figure out the, let me reset my, oh, well, we had a question. Why did we not have a minus 1 as part of the range? We did have minus 1 as part of the range, so that was this here. Remember, you subtract. The minus 1 squared is just 1. So minus 1 squared, because you plug that into x squared, and minus 1 squared is 1. Okay, but anyway, let's try this out. Let me reset my chat. No. The inside integral doesn't have to always be x. Sometimes it's x, sometimes it's y. You need to pay attention to that. This is why, remember when I was saying this dx or this du or whatever the variable that is, that's important, because the inside integral is whichever one of them is first. Okay, looks like we're starting to get some replies. We're getting a lot of A's. So let's try working this out and see what happens. So the first step is we want to do this inside step, right? And you have to be a little bit careful when you're doing this inside step. So this is the integral from minus 1 to 1 of 2y dx, right? So what does this equal to? Well, you treat y as a constant, right? So this is, if it's a constant, you could think about moving it out in front. But basically, when you treat it as a constant, what you get is you get 2xy from x is equal to minus 1 to x is equal to 1. And let's see. Oh, sorry. Looks like we got a couple other answers. So from x is equal to, so this is equal to 2 times 1 times y minus 2 times minus 1 times y, which is equal to 4y. And now we need to do the outside step using 4y. So when we do this outside step, that's the integral from 0 to 2 of 4y dy, which is equal to 2y squared from y equals 0 to y equal to 2, which is equal to 8 minus 0, which is equal to 8. So the answer here is actually C, which it looks like most people did not get. So you have to be careful what you're integrating with respect to. When you're integrating with respect to x, you treat y as constant. When you're integrating with respect to y, you treat, well, you shouldn't have, in this particular case, you shouldn't have any x's left, because you already integrated them out. Okay, do we have any questions about that? It seems like there were a couple problems. There will be practice problems for this sort of thing, and we'll show you a couple more examples. So hopefully this will be a little bit more obvious. But in this case, the answer was actually 8. Okay, so people also asked. Oh no, my notes are. Oh no, my notes are. Wait, are my notes right? Okay, so on the last slide we had this integral, right? 2y dx dy. Oh, question: should we be able to do these quickly like the regular integrals? Yes, you should. But the way to think about it is these are exactly the same. Yes, exactly. So if dx is the inner part, then that is done first. So now, what happens if I give you this question? What happens if I switch the order? And note that when I'm switching the order, I also switch the limits, because the limits correspond to the... so it looks like there's a little bit of confusion. That's all right. So basically, when you're doing this integral, the first thing you do is you take this entire piece out first. You solve that, and then you plug that back in and solve the rest of it. So you're just doing integration twice, but each time you're doing it, you have to pay very careful attention to what variable you're integrating over. So this is why it's super important to pay attention to this ordering. But now, I was just asking, what happens if you switch the order of the integral? In this case, note that here, in this case, we're doing dy first, and then we're doing dx. So what does this equal to? So when you take, let's do the interior piece first. So that is just going to be the integral from 0 to 2y dy. So that's equal to y squared from y equals 0 to y equal to 2. And that's equal to 4 minus 0, which is equal to 4. And if you do the other piece, from minus 1 to 1 of 4 dx, that is equal to 4x from minus 1 to 1, which is equal to 4 minus 4, which is equal to 8. And so you did actually get the same answer in this particular case. And note that we can often switch the order of integration and get the same answer, but this is not always true. So remember how what I said with the partial derivatives, usually you can switch the order of the derivatives? Usually you can also switch the order of the integral, and it will still work out. But note that when you're switching the order of the integral, you have to make sure, note that these things also have to switch with the order. So be careful about your limits. And if you're ever confused about the limits, what you can do is you can write this out. Let me do this in a different color. You can write this out by explicitly specifying what variable the limits correspond to. Okay? Does anyone have any questions yet? Yes. So you do the inside part first, and then you do the outside part. And you can just treat it as two completely separate integral problems. You do one first, and then you plug in that answer into the other one, and you do that one separate. Yeah, no, it is a lot of information to digest. And yes, I am throwing basically all of multivariable calculus at you in one day. So don't be concerned if it seems like a lot of information, because it is a lot. There are entire classes that are focused on multivariable calculus, but we're not going into the theory behind it. We're just giving you a bunch of techniques, and it is a lot for one day. And I'm about to throw even more information at you. So you have to be really careful. So sometimes you can swap the order of the integrals, sometimes you can't. And this is one major case where you can't, which is you can use the outside integral variable in the limits of the inside variable, but not the other way around. So let me try to go through this slowly. Stop me when you get confused. So let's say I had the integral from 0 to 1 of the integral from x to x squared of xy squared dy dx. Okay, so now what is this? This is weird, right? Because you have the x's in the limits as well for the y integration. But remember, this is fine, because when you do this integral, you treat x as a constant. So when doing, treat x as a constant. So this is really what we're saying here is, for this blue part, is the integral from y equal x to y equal x squared, where x is just some constant. So now, stop thinking about x as a variable. For this problem, x is some random constant like 1 or 2 or a or b. And so then you have xy squared dy, and this is going to be equal to, well, you're integrating with respect to y, so this is 1/3 xy cubed from y equal x to y equal x squared. And when you plug in x squared for y, what you end up getting is x to the 7th over 3 minus x to the 4th over 3. And when you do the rest of it, which I'm going to do in green, what you're going to end up getting is, oh, I'm going to run out of space, aren't I? Let me do this here, so I have 2 lines. So this is going to be the integral from 0 to 1 of x to the 7th over 3 minus x to the 4th over 3 dx, since we're just plugging that in. So we're plugging in the blue part into the integral for, so you should think of this as equal to the integral from 0 to 1 of blue stuff dx. So we plugged in the blue stuff. And now this is going to be equal to, I'm going to rewrite it to make it a little bit easier. So I'm going to pull out the 1/3 in front. So 1/3 integral from 0 to 1 of x to the 7th minus x to the 4th dx. This is equal to 1/3 times 1/8 x to the 8th minus 1/5 x to the 5th from x equals 0 to x equal 1. And this is just a matter of plugging in numbers. So this is 1/3 times 1/8 minus 1/5. And of course, when x is equal to 0, the entire thing is equal to 0. So if we plug this out, this is just solving fractions. 1/8 times 5 over 40 minus 8 over 40. This is equal to 1/3 times minus 3 over 40, which is equal to minus 1 over 40. Okay, so note that the only reason we were able to do this is because the x variable is treated as constant. So you can use the outside variable in the limits of the inside variable, but you can't ever do it the other way. So you can't swap these integrals. It just won't work. Okay, so let's have y'all try this out. And let me go ahead and get it set up for you a bit. So the first thing to do is you take this piece, this blue piece, which is going to be the integral from x equal 1 to x equal y squared 2x dx. And then you're going to do this green piece, which is going to be the integral of whatever the stuff you ended up with in the blue here for 0 to 2 of dy. Okay, and let me reset my responses and give you guys a moment to try to solve this one. And so the trick is just to keep them completely separate. Okay, so it looks like we're starting to get some responses. Okay, so we're starting to get a number of responses. Okay. Looks like most people think it's B, and I think we have 1 or 2, just 1 C. So let's actually go through and walk through this together. This thing is equal to, well, the integral of 2x dx is just x squared from 1 to y squared. So this is equal to y to the 4th minus 1. And then you plug this entire thing in. So this is equal to the integral from 0 to 2 of y to the 4th minus 1 dy, which when you plug the entire thing in, that's going to be equal to 1/5 y to the 5th minus y from 0 to 2, which is going to be equal to, well, 2 to the 5th power is 32. So 32 over 5 minus 2. And when you plug in 0, you're just going to get 0. So this is going to be equal to 22 over 5, which is indeed B, which is what most people manage to get. Okay, so this is how you mechanically do these multiple integrals, but what does it mean? And here, I'm going to just end with this interpretation of it just to give you a sense of what it means. multivariable functions can be thought of as these surfaces, right? So that's what we were doing in the very first part of lecture today. Now, when you think about it, single variable functions are these curves in the plane, right? And the integrals are the area under the curve. These double integrals correspond to the volume under the surface for a particular region. So if you have this surface in space and you set your x and y bounds, so that's why you have your limits of integration, one of which are the x bounds and the other of which are the y bounds. When you set those limits, then you're specifying a particular region in the plane, and you're looking at the area under the surface for a particular region. And this is a geometric interpretation of this multiple integration. The most likely place you guys are going to see this is maybe if you take a probability and statistics course. It turns out that often when you're looking at the probability of something happening, you need to use these sorts of double integrals to figure out what the probability, how much probability there is underneath a particular curve. But that is a much more advanced topic, which I don't think we're going to get to in this class. But I just wanted to give you guys some intuition. So these double integrals are volumes, basically. They're another way of getting volumes from an integral. Last time we had the volumes of integration. Volumes of revolution. By last time I mean like 3 weeks ago. In this particular case, you can still think about the volume underneath a surface for these multivariable functions. And with that, I think I will end this class a little bit early. I know we're 5 minutes early, which we're never early, but this was a lot of material, so if you have any questions, feel free to ask me after class, and I'll try to stick around and answer some of them. So thank you very much, and on Friday, we're going to be talking about applying some of these things to find the maximums and minimums of multivariable functions. And then later next week, we'll get to things that are actually quite applicable for mathematical biology, which include things like doing regression analyses and least squares. So if you have a bunch of data, how do you fit a function? And that turns out to be something that we need to do for, that turns out to be really important for a lot of biological data analysis. There's a question, can we simply use the volume formula? So this is using the volume formula for these arbitrarily shaped curves, because there are several different types of volumes, right? So this is a particular type of the volume underneath a surface. Whereas the last time we did volumes as a revolution, or like volumes where each of the individual pieces along one dimension had a particular area. So these are slightly different ways of thinking about volume. So anyway, I am going to end the recording here, and I'll stick around a little bit if you guys have more questions.